The hydrohalogenation reaction is probably the most prototypical alkene addition. Keep watching, because there's a lot more baked into this simple reaction than you might be expecting. The hydrohalogenation reaction might be the first reaction you learn in the alkenes chapter, and there are some good reasons for that. It's a fairly straightforward reaction that demonstrates a lot of the principles we need in this chapter. But stay tuned. I'm going to show you how to use the skills learned in this reaction as a cut and paste template that you can use in all of your reactions to make sure you draw the right product. To start, let's break down the word hydrohalogenation. The hydro part refers to a hydrogen. It doesn't refer to water, that would be hydrates, and the halogen refers to a halogen, a bromine or a chlorine or an iodine. So in the hydrohalogenation reaction, we're adding a hydrogen and a halogen across the alkene. As a pattern recognition, the net reaction tells us that hydrogen likes its friends. The hydrogen of the HBr will end up on the same carbon with the most other hydrogens. Before we dig into the mechanism, let's take a look at a couple of reaction notes. The hydrohalogenation I classify as a type 1 electrophilic addition. That's a distinction that I invented. If you'd like to know what I mean by that, I have a video that I'll link to in the description below. This reaction follows Markovnikov's rule. When the alkene reacts, it will react to form the most stable carbocation possible. If you'd like a refresher on that, I also have that video linked below. As we go through the mechanism, we'll notice a carbocation intermediate will form. We need to have a Pavlovian response every time we form a carbocation. We need to check for rearrangement. If you don't feel confident with rearrangement, I have that video that I'll link below as well. And one other note that we'll tuck away for later, that carbocation intermediate is flat and trigonal planar and sp2 hybridized. In terms of the mechanism, if these two molecules are reacting, one of them will have to be the nucleophile and the other will have to be the electrophile. What I notice is the HBr. HBr is an acid. The hydrogen has a large partial positive charge because it is a strong acid. With a large partial positive charge, that means it lacks electron density, and that means that HBr is going to act as the electrophile in this reaction. Specifically, it is the hydrogen atom in particular that is the electrophilic atom. If HBr is the electrophile, that means the alkene must be the nucleophile. Specifically, thanks to Markovnikov's rule, we know that the terminal carbon, the less substituted carbon, will be the nucleophilic atom of the alkene. This first step will be a reaction between the nucleophilic carbon of the alkene and the electrophilic hydrogen of HBr. To draw the arrows for the first step of the mechanism, we need to start our arrows at a pair of electrons. The electrons are in the carbon-carbon pi bond right now. We'll start our arrow at the pi bond. We'll take this arrow from the center of the pi bond and bounce it through our nucleophilic carbon to attack the acidic hydrogen of HBr. Arrows tell a story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. Specifically, this arrow is saying we're breaking the carbon-carbon pi bond using the electrons that used to be shared between these two carbons. Carbon number 1 gets to keep those electrons and use carbon number 1 to form a new bond with the hydrogen. This is an example of bouncing arrow notation. If you're not familiar with bouncing arrow notation, I can link you to that video that I have down below. So this arrow says we're forming a new bond between carbon number 1 and hydrogen, but hydrogen only makes one bond. This starts to build up too much electron density around hydrogen. Not a big deal. We just take the electrons in the HBr bond, we break the HBr bond, and push those electrons onto bromine locally as a new lone pair of electrons. Arrows tell a story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. This arrow says we're taking the electrons that used to be shared between hydrogen and bromine, breaking that bond, taking those electrons and localizing them locally onto bromine as a new lone pair. The result of this step will be our first intermediate. We'll break the pi bond on carbons 1 and carbon 2. Carbon 1 will form a new bond with hydrogen. Carbon 1 in this example already had two hydrogens attached. We don't have to draw them in, but if it helps you see where all the hydrogens go, you're certainly welcome to. But we're not done with this structure. In order to break the pi bond and allow carbon 1 to use those electrons, we had to take the electrons away from carbon number 2. That means carbon number 2 is now electron deficient and needs a full positive charge, a carbocation. This is the intermediate after step 1. But I just want to pause and sit here for a second. I want to give you a template, a frame of mind to think about every step in the mechanism to make sure you're getting it right every single time. Whenever we draw intermediates in a mechanism, I always like to ask myself 3 questions after every single step. And those 3 questions are, do I have all of my charges in carbons? Can I stabilize this intermediate by resonance? And is that step that I just did reversible? If we ask ourselves those questions every single time after every single step in a mechanism, we'll be on our way to make sure we're drawing the mechanism correctly. Our first question, charges in carbons. Let's give this molecule a numbering system so we can follow along with our carbon numbers throughout the reaction. There are 4 carbons in the starting material. You should make sure you have 4 carbons in your next intermediate. But what about charges? We started out net neutral, 2 neutral molecules reacting, and now we have a net positive charge. It seems like we don't have our charges balanced. For every single reaction in organic chemistry, every single step must have a charge balance. The net charge on the reagent side needs to be the same as the net charge on the product side. So what's going on here? Why are we net positive on the product side? And it's because we haven't quite drawn in everything. When the HBr bond breaks, the bromine leaves as Br- leaving group. The Br- with the carbocation is net neutral. We are net neutral on the product side of this step. This happens a lot in organic chemistry. The leaving group we leave has some kind of charge that balances out the charge of the major organic product. Sometimes we'll draw it in because it will be important in the rest of the mechanism, and sometimes we'll omit that counter ion because it's just not that important. As organic chemists, we always know it's there, we just don't always draw in the counter ions. You, of course, are welcome to draw them all in if it helps you see that the net charge is conserved, but your instructor might not draw in the counter ion all the time, and I probably won't in all of my videos. The next good question to ask after every step in a mechanism is this intermediate stabilized by resonance? If an intermediate is resonance stabilized, it's a good idea to draw out those resonance contributors. If you were taking my course, I would expect you to show the resonance stabilization of any intermediate. So what about this intermediate? Can this intermediate be stabilized by resonance? No. Not this one. This one cannot be stabilized by resonance. Sometimes the intermediate will be resonance stabilized, sometimes it won't. We just have to check every time. The last good question we should ask ourselves every time is this step reversible? To answer that question, we ask ourselves what happened in the forward direction and what would that have to mean for the step to be reversible? In the forward direction, we have a nonpolar pi bond attacking a mineral acid. This is known as an electrophilic addition step. There are certain criteria that have to be met for reagents to be able to do an electrophilic addition. The nucleophile needs to be a nonpolar pi bond, a pi bond between two carbons, either an alkene or an alkyne. And the electrophile needs to be an acid that is sufficiently acidic. Specifically, it needs to be an acid with a pKa less than around 4. So carboxylic acids can't really do electrophilic additions, but anything stronger than a carboxylic acid, such as a mineral acid, can do an electrophilic addition. So in the forward direction, the pi bond broke and carbon number 1 formed a bond with hydrogen, kicking out bromine as a leaving group. So in the backward direction, the Br- would have to act as a base, taking this hydrogen, reforming the pi bond. That would be called an electrophilic elimination. To do an electrophilic elimination, the base needs to be a sufficiently strong enough base to take this hydrogen and reform the pi bond. And the conjugate base of mineral acids are not sufficiently strong bases. The Br- is very stable, very weak base, not basic enough to take this hydrogen and reform the pi bond. The conjugate acid of the base needs to have a pKa greater than 0 or so. Since Br- does not fit that condition, no, this step is not reversible. Some will be, some won't be. We'll have to check every time. Now that we've asked ourselves our good questions, now we're ready to go on to the next step of the mechanism. If you ever get stuck in the middle of a mechanism, you can look at the molecules you have and reassess. Where's the nucleophile? Where's the electrophile? I see the negative charge on bromine. That means bromine negative charge is likely to be a nucleophile, with bromine being the nucleophilic atom, which means the carbocation must be the electrophile with its full positive charge. Specifically, carbon number 2 is the electrophilic carbon. Nucleophiles attack electrophiles, so the lone pair on bromine can form a bond with carbon number 2. Arrows tell a story. They tell the story of the movement of electrons. They tell the story of old bonds being broken and new bonds being formed. This arrow says we're taking the lone pair that used to be localized on bromine, and now we're sharing those electrons with carbon number 2 to form a new bromine-carbon bond. The result of this step will be our carbon chain with a new bromine attached to carbon number 2. Now that we've finished the step of the mechanism, we should ask ourselves our 3 good questions. Charges and carbons. Our intermediate has 4 carbons, and our product has 4 carbons. Make sure your product has 4 carbons as well. In terms of charges, we are net neutral on the reagent side, and we formed 1 neutral product on the product side. Yes, our charge is balanced. How about resonance? We don't typically draw resonance for products. That's typically just for intermediates. And 3, what about it being reversible? In the forward direction, we had a coordination step where a lone pair attacked an empty orbital. The reverse then would be breaking the carbon-bromine bond and giving those electrons back to bromine to leave as a leaving group. That would be heterolysis, the spontaneous leaving of a leaving group. For a heterolysis to be a valid step, the leaving group would have to leave as a very stable leaving group. Typically, we would think about it as a weak base being a good leaving group. The group that leaves need to have a conjugate acid with a pKa less than about 5 or so. Here, the group that leaves would be Br-. Br- conjugate acid is HBr. HBr is a very strong acid, much less than 5 pKa. So yes, this step is reversible. We would depict that by drawing reversible arrows in our mechanism. Now that we've drawn the product, we can ask ourselves one more very important question. Does our product have any new stereocenters? If we look through our product here, carbon number 2, yes, is a new stereocenter that was not present in the original molecule. We need to determine the stereochemical consequence of this reaction. What kind of stereochemical product are we making? Is it going to be achiral, a mixture of enantiomers, a mixture of diastereomers, a mesomolecule? What is the stereochemical consequence of this reaction? The best way to determine the stereochemistry of your product is to go backwards through the mechanism until you find the step that formed that stereocenter. For this reaction, as we go backwards, that carbon-bromine bond formed here in carbon number 2, this is the step that formed that stereocenter. By analyzing this step of the mechanism, we can figure out the stereochemical consequence of this reaction. And what we need to see for this reaction is that carbon number 2 is sp2 hybridized. There is a hidden hydrogen on carbon number 2. That's 3 electron domains around carbon 2, so it is sp2 hybridized with the carbocation. If we look at the orbital picture of carbon number 2 is using its sp2 hybridized orbitals to form bonds with carbon number 1, carbon number 3, and the hydrogen. It also has the unhybridized p orbital that's perpendicular to the 3 sp2 hybridized orbitals' trigonal plane. The 3 sp2 hybridized orbitals are all in one plane, and the unhybridized p orbital is perpendicular to that plane. And it's this unhybridized p orbital that is empty, and that's where the carbocation is. Why is that important for this analysis? Notice that the p orbital has a lobe above and below this plane. So when the Br- attacks, it could either attack the top lobe or, without preference, the bottom lobe indiscriminately. That means we end up with a mixture where the bromine is on top about half the time and on bottom of the molecule about half the time. So as drawn, this would be an incomplete drawing of our product. The most complete way to show the product of this reaction then is to draw the version where the bromine is on the wedge and the version where the bromine is on the dash. What is the relationship between these molecules? There's one stereocenter, and that stereocenter changes its orientation in the two molecules. All one of the stereocenters have changed their orientation. These molecules are enantiomers. This is one way to draw the complete answer to this question. Another valid way you could draw the product of this reaction is to draw one version of the product and mark the stereocenter, and then you could write one of three things that would let your instructor know that two different versions of this product form. You could write plus enantiomer, not tenant. We're not renting out our stereocenters. Plus enantiomer lets your instructor know that this molecule and its enantiomer form in about an equal ratio. You could also draw one version of the molecule and write the word racemic. Recall that the definition of racemic is a 50-50 mixture of enantiomers, and that's exactly what forms in this reaction. The third way would be to draw one version of the molecule and write plus minus. That's an alternative way of writing racemic. It refers to the optical rotation of chiral molecules. If one version of the molecule rotates plane polarized light in one direction, the enantiomer will rotate plane polarized light the same magnitude but in the opposite direction, the plus and the minus version of the molecule. But however you choose to do it, you need to let your instructor know that you know the stereochemical consequence of the reaction. So if we take a step back for a second, the hydrohalogenation is actually a fairly straightforward reaction. First, the alkene does an electrophilic addition to form a carbocation. Then that halogen leaving group forms a new bond with the carbocation to form our halide product. But by taking the time to go through all of these questions for every step of the mechanism, this is a template. You can cut and paste this template to every reaction we do in the alkenes chapter and beyond to make sure you're drawing the correct intermediates and the correct product every single time. Every time you draw a new structure, do you have all of your charges and carbons? Can this intermediate be stabilized by resonance? Is this step reversible? And when you get to the product, did I form any new stereocenters in my product? This takes some of the memorization out of mechanism. By forming a mindset for mechanisms, we don't have to memorize every single mechanism. We can reason our way from one step to the next. This was a fairly low ninja level example. In a companion video to this one, I walk through the hydrohalogenation in 5 ninja levels of difficulty, ranging from the fairly straightforward to the actually fairly complicated with a couple of nuances. When you are done with this video, you should watch that companion video that I've linked in the description below. This is a powerful template. If you can internalize this template and apply it to future mechanisms, you are well on your way to being an OChemNinja. What about you? Which step in this mechanism is the most confusing for you? Leave me a comment down below and I'll help you out. Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.